Hello everybody, so we are in MAT 1350. I promised you last time that I will say very vague words on how the integrals from the previous time or the cosmic coincidences from the previous time come from quantum field theory, and I only want to say it very vaguely. If I wanted to say it in any more detail, it would be a whole semester. Okay? So the idea, which is Witten's, so it's due to Ed Witten, but it builds on this particular earlier form, which is due to Chern and Simons. Is the following. So the way we, maybe even before that, so, if you have a geometric knot, like if you have an actual curve in R3, there are lots of ways to get invariants. Namely, you could, compute the curvature of this line at every point and integrate it over the knot. Sorry, except that's not to get quantities, right? That's actually not an invariant. It's because, it changes if you deform the knot. But for every specific knot, for every specific embedding, for every specific curve, it's a quantity. And then the idea of topological quantum field theory is that you look at such quantities and you average them over all possible choices of geometries. So the quantity depends on the geometry, and you average over all possible choices of geometries, and then you get something that no longer depends on a choice of a geometry. The problem is that the space of geometries is infinite dimensional, so you need to use weird techniques that don't always work in order to make sense of what I said. And perhaps the best example of a situation in which this idea works is this Witten-Chern-Simons theory. Okay? So Witten says the following. So given a curve gamma, so here the curve gamma appears in this formula only once, and it's this one, a knot. So given a curve gamma, you choose a so-called connection A, but a connection for our purpose is just a one form on R3 with values in the Lie algebra. So a one form generally is something that takes 10 tangent vectors to numbers, and instead we will look at something that takes tangent vectors into the Lie algebra, and if you really want, you can think of it as if it's a Lie algebra of matrices. Okay? So we want to, so given a one form, we construct an integrand. And the integrand is a pretty messy thing. So it's the exponential of, ik over 4 pi. K is some parameter, let's not think about it too much. I is the square root of -1, 4 pi you know. And then the integral over R3 of the trace of a wedge dA plus 2/3 a wedge a. So let me explain what this means. So if you have a one form, dA will be a two form, and then a wedge dA will be a three form, except since A is valued in the Lie algebra, a wedge dA will also be valued in the Lie algebra instead of in the reals. So this whole thing here will be valued in G tensor G. And then trace is just a different name for the inner product that we assume we have on our Lie algebras. So once you compute the inner product of, right, if you have two factors in the Lie algebra, you compute the inner product, you get something valued in the reals. This something is the wedge of a 1 form and a 2 form, so it's a 3 form. And since it's a 3 form, you can integrate it on R3. Similarly, A wedge A wedge A is, so A is a 1 form, A is a 1 form, A is a 1 form. So altogether you get a 3 form. It is valued in G tensor G tensor G. And we actually also have a functional from G tensor G into the reals, and by abuse of notation, we also call it trace. Okay? And the functional is, well, if you want, it's contraction with the structure constants that were made to have all the indices up. So if you want, it's contraction with FABC. If you want, a different way to say it is to say that you take the bracket of the first two factors and inner product it with the third. Okay? So anyway, this is something that's integrated over R3, and then you exponentiate it and multiply, and this is actually completely independent of the knot. So you exponentiate it and multiply it by with the holonomy along the knot of the connection A. So let me explain what this is. So suppose again we have a knot. Now remember, we have we have a 1 form with values in the Lie algebra. So if I look over the knot, if I look around the knot has a tangent at every place, at every point. So on every point, you can evaluate the 1 form on the tangent, and then for every point along the knot, you get an element of the Lie algebra. So you get x1 here, x2 here, x3 here, and so on. Now, elements of the Lie algebra are infinitesimal elements of the group. So what you do is you multiply those infinitesimal elements of the group along the knot, and then you get a global element of the group. And maybe I should have said, sorry, when I wrote it I had something else in mind. So you take a global element of the group and then you take its trace in a representation, and you get a number. Okay? So what does, by the way, multiplying all these elements along the knot is roughly integration made multiplicative. So integration is summation is continuous summation. So basically this is the same but continuous multiplication. Okay? Anyway, I don't want to say much about it because again, that's a long story, but I want to observe a few things. First of all, the metric never played a role. The metric properties of R3 never played a role. I never needed to measure distances because integration of 3 forms is independent of a choice of a metric. The 3 forms are kind of come with their own measure. And similarly, I didn't define holonomy sufficiently well, but really well, it's really the integral of a one form, so it does not depend on distances. Okay, it's a canonical quantity. So this whole thing, at least naively, if you could ever make sense of it, so this whole thing does not depend on metric properties, so on distances and things like that. But that just makes it topological invariant. So this is what it means, that it's a topological invariant. And I'm admitting that I'm cutting corners. Oh, and I had the usual thing that I failed to disable the program that's running in the background. Sorry, so that's 1 minute. Okay, now it is disabled. Sorry about that. Okay, so so that's that's the good news. The bad news is that it totally doesn't make sense. Okay, because the space we integrate on is the space of one forms with values in Lie algebra, A one form is essentially a triple of functions, right? If you have a one form, so if you have a one form A, you can always write it as f1 dx plus f2 dy plus f3 dz. So it's a triple of functions. Each function is a function on R3 with values in the Lie algebra. So it's really an integral over a space of functions, in fact of triples of functions. Okay? And that's an infinite dimensional integral. There is no Lebesgue measure. You can prove that there is no Lebesgue measure. So you can prove integration theory doesn't make sense, so we're dead. Or at least it seems we're dead. So that's bad news. Okay? So, I mean, not only this is infinite dimensional, so this space here, the circle thing here, this space, not only it is infinite dimensional, in fact it is uncountably many dimensional. So it sort of has, if you have a function, you can choose its value at each point, which means that you have uncountably many choices. So it's really an integral over something whose size is comparable not just to r to the n, but to r to the r. It really doesn't make sense. Okay? Now here is the good news, so more good news. So if you look at it very carefully, you can expand this as a power series in A. So really you can think of it as a polynomial in A, but sort of an infinite polynomial. So this part is a polynomial in A, and this part looks like the exponential of something which is quadratic in A. So this part depends on A quadratically, and this part depends on A like a cubic. Okay? So why is this good news? The good news, it's good news because now I could switch to my next screen and say to myself, maybe we can develop techniques to compute the integral of an exponential of something quadratic plus something cubic. Okay? And in fact, I could have inserted here a polynomial, so maybe a polynomial times something quadratic plus something cubic, but the polynomial we can insert at the end. It really, it makes little difference. So, so again, I want techniques for computing the integral of something quadratic plus something cubic. If I am lucky, And you know, this is not the kind of luck that you could have anticipated. This is the kind of luck that happens when people play with things for 100 years and get to know them and eventually find, you know, and eventually find the luck. Okay, so I'm not really deriving. It's more like I'm summarizing what happened over many years. Okay, but anyway, if I am lucky, if we are lucky, then this integral you will be able to evaluate, to compute, and write it as a sum. So maybe multiple sum. So maybe you will be writing it as a sum. I don't know why I started with j. Okay, fine, whatever. Sum j goes from 1 to n because it's an n-dimensional integral. Of sum I goes from 1 to n. Of sum k goes from 1 to n. Maybe you could re-express it as a sum. And then of some expression that depends on I, j, and k. Maybe you could do that. And if you could do that, then you'd want to replace r to the n by r to the infinity. Or more precisely, replace the integer n by the real numbers, by something on the size of the real numbers. And then summation of from 1 to n will become integration d, a variable corresponding to j, so dj maybe I'll call it. And then summation as I goes from 1 to n will become integration di. Summation as k goes from 1 to n will become integration dk, and then you'll just copy the expression. Ijk. Now, the whole process didn't make sense, but the end result, if you're lucky, does make sense. Okay? Because now we just switch down to integration over a finite dimensional space. Okay? So again, the lucky thing that happens is that integration over Rn becomes summation depending only of indices that runs from 1 to n. So it makes sense to substitute n is equal to infinity and pretend that when you do such integration on an infinite dimensional space, it becomes a combination of finite dimensional integrals. So let's do that. Okay? So, suppose lambda ij is a positive definite matrix. I want it to be positive definite so that the exponential of e to the minus 1/2, basically so that this will converge. Suppose lambda up ij is its inverse. This is our usual convention. Suppose lambda ijk is a triple tensor, which makes the coefficient of a cubic form. So if you look at sum of lambda ijk, x to the I, x to the j, x to the k, sorry, that's not x to the power k, it's x, the ith component of x, the jth component of x, the kth component of x, then this is a cubic polynomial on r to the n. For use later, let ti be variables dual to xi, and let derivative up I denote the derivative with respect to ti. And finally, I need one constant that will be used later, so let's call it that constant. Okay? So, so now my goal is to try to compute this integral. And let's also assume that in some sense the cubic part is smaller than the quadratic part. So in some sense, I don't know, maybe the coefficients of the lambda ijk are small. Okay? So then what I do is I rewrite this as a product of exponentials, and I pretend that this exponential, being the exponential of something small, is somehow close to 1. So this is near 1. Okay? And now I need a little bit of background from Fourier analysis. Okay? So the Fourier transform, I hope you've seen it, is defined on any vector space, and it takes functions from functions with functions on a vector space with values in the complex numbers to so-called f tilde, where f tilde is a function on the dual vector space with values in the complex numbers. And typically, you think of the vector space as being Rn, and you're a bit careless, and you think of its dual as also being Rn. Where the definition is as follows. So, the Fourier transform evaluated on a linear functional is equal to the integral over the original space, the vector space, of the function fv, f of v. Oh, this should have been uppercase f. Maybe this should have been lowercase f, sorry. So, the function fv multiplied by e to the minus I, the pairing of phi and v, integration dv. Okay? By the way, you just saw an example why it's better to write the integration variable before the function, right? You declare what you're going to do ahead. I mean, basically compare this with the formula that you're probably familiar with, which says that f tilde of p is equal to the integral of f of x e to the minus I px. So if you're doing it on a general vector space, p must be dual to x so that you can pair p and x, and the pairing is, well, and I've switched language, so the pairing here is phi and v. Okay? Now, a few properties of the Fourier transform. So, the Fourier transform evaluated at 0, so if phi is the evaluated at 0, well, then here you get the exponential of 0, so it's 1, so you just get the integral of f of v. Property 2, so this is, again, I'm hoping you've seen the Fourier transform before, but property 2 says that the derivative with respect to phi of the Fourier transform is the Fourier transform of v multiplied by f. Maybe you've seen it in the here as the derivative with respect to p of f tilde is equal to the Fourier transform of x times f. Okay? So basically, the Fourier transform takes multiplication by x to differentiation, multiplication by one variable to differentiation with respect to the dual variable. And sorry, I wrote equal, but I really meant proportional. There is some constant of proportionality which I don't want to figure out what it is. It's I or minus I or something like that. Okay? And finally, so if you take the Fourier transform of a Gaussian, what you get is a proportion, namely the exponential of a quadratic. What you get is the inverse Gaussian. Okay? So, you might have seen it in the language, or you might have seen it written as the Fourier transform of e to the minus lambda x squared over 2. So, the Fourier transform of this is equal to, or not equal, sorry, proportional to, with some fixed constant of proportionality, it's e to the minus p squared over 2 lambda. So the coefficient of the quadratic gets inverted. Or said differently, the Fourier transform of, so think lambda is large, then this is a very sharp Gaussian. And the Fourier transform of a very sharp Gaussian is a very shallow Gaussian. And vice versa. And by the way, this is the key to one of the proofs of the Fourier inversion formula. So you probably know that the Fourier transform squared is more or less the identity, right? Actually, it's the symmetry that replaces x by minus x. Okay, but I mean, more or less, if you do the Fourier transform twice, you go back to where you started. And one reason why this is true is because it's true for Gaussians by explicit computation. And then Gaussians are more or less a basis for all the functions. So if you take a Gaussian, you can write any function as a combination of Gaussians that are translated, well, I mean, my Gaussians no longer look like Gaussians, but basically you can write any function, or at least approximate any function, by as a combination of translated Gaussians. And the reason is that, well, a Gaussian is roughly an approximation to a delta function. So any function can be written as a combination of translated Gaussians. And then, since the Fourier inversion formula is true for Gaussians, and it's linear, so it's true, and then you can check that it follows that it's true for translated Gaussians and for linear combinations of translated Gaussians, and therefore it's true everywhere. So that's one sketch of a proof of the Fourier inversion formula. Anyway, in our case, where the quadratic is given by a matrix, so instead of a single lambda, we have lambda ij. So in our case, where the quadratic is given by a matrix, maybe I'll do it here, then e to the 1/2 lambda ij xi xj Fourier transform will be proportional to the inverse, to the Gaussian given by the inverse matrix. So e to the 1/2 lambda up ij, right, that replaces the 1 over lambda that we had before, ti tj, where the t's are the dual variables to the x's. Okay, good. So we are, well, believe it or not, we made progress. So what we had was the integral of a power series, right? Think that this is, so since that the x's are small, so I could have expanded it as a power series in the x's. So it's as if I'm integrating a polynomial in the x's times a Gaussian. Well, how do you integrate? You compute the Fourier transform and evaluate at 0. So I need the Fourier transform of lots of x's multiplying a Gaussian. By the second formula here, the Fourier transform of multiplying the function by the variable, by the x's, is like differentiating with respect to the dual variable. And by the third formula, the Fourier transform of a Gaussian is the inverse Gaussian. So therefore the conclusion is that all we need to do is to replace the Gaussian by the inverse Gaussian, apply to it the differential operator which is the exact same. So basically you take the polynomial in the x's that was written here, or power series, and replace every x by differentiation with respect to the dual variable. Integration was evaluation at 0, so I need to evaluate all of this at 0. And finally, there is a constant of proportionality, which we call it C, but in fact it's the same C that I've defined before. It's some power of pi multiplied by some determinant of lambda. Okay? Now, again, I don't know if you appreciate it or not. We have made a tremendous achievement already, because we had an integral and the integral is evaluated. There is no integration anymore. What's left is pure algebra, right? What's left is evaluating a fancy differential operator on a fancy quadratic, exponential of a quadratic, but and then evaluating everything at t equal to 0. But this is algebra. We no longer do Riemann sums. We no longer need to know the name Lebesgue or anything like that. So this could make sense in infinite dimensions. Okay? But anyway, let's compute this. So basically, I write each exponential as a power series. I expand each exponential. So the exponential of 1/2 lambda alpha beta t beta becomes a sum as L goes from 0 to infinity of the input here raised to the power L. The 2 is also raised to the power L, it just appears here. Okay? Divided by L factorial. Here is the L factorial. And the exponential of 1/6 lambda ijk del I del j del k becomes a sum as m goes from 0 to infinity of lambda ijk del I del j del k to the power m divided by m factorial, and the 6 to the m here is also appearing, and well, I also copied the c. One extra bit of information. So this is a certain function of the t's. I apply to it a differential operator which differentiates with respect to t. If I look at any specific term here, which has t to some power, if I differentiate, say I expand this and I get t to the 17. Actually, I'll never get t to the 17 because it must be even. So t to the 18. So suppose I'm looking at the terms that looks like t to the 18 in this expansion. If I differentiate it more than 18 times, I'll get 0. If I'll differentiate it less than 18 times, I'll have a leftover t, right? I mean, if you differentiate t to the 18 16 times, you get something that's proportional to t squared. But at the end, I evaluated that the t is equal to 0. So the number of differentiations must be equal precisely to the number of t's if I want to get a contribution. Okay? So therefore I've removed this evaluation, and instead I've added the condition that the number of differentiations, so this is 3 times m because each factor here has 3 differentiations, should be equal to the number of t's, which is 2 times L, because again, the number of t's here is twice L. Okay? Now, you can complain. You can complain that this is horrible mess. You can complain that this is ugly. You can complain that this is a meaningless formula. Complain as much as you wish. It's still a major achievement because again, we have still just reduced an integral to algebra. Okay? Okay, but now let's try to interpret this. So, summation I've copied, the factors I've copied, and now I want to understand the differentiations and how the differentiations act on these pairings, on these quadratic raised to the power L. Okay? So, okay. So, what is a quadratic raised to the power L? Let me symbolically denote it by having L copies of the quadratic. Okay? In each copy, so you know, if you have a sum raised to the power L, then it becomes a multiple sum, right? Where over L variables, right? This is the distributive law, right? If you take a sum raised to the power L, then it's or you know, if you have a sum over alpha and beta, and you raise it to the power L, then the distributive law means that it becomes that you can rewrite it as a sum over alpha 1 up to alpha L, and then beta 1 up to beta L of whatever terms you had here, you take L of them, you make L copies. Right, that's the distributive law. So basically I replace lambda alpha beta t alpha t beta with lambda alpha 1 beta 1 t alpha 1 t beta 1 multiplied by, so there is an implicit multiplication here, lambda alpha 2 beta 2 t alpha 2 t beta 2 multiplied by, so basically this thing here is an expansion using the distributive law of what is written here. Similarly, but let me erase this, okay. Similarly, the thing at the bottom is an expansion of, so lambda ijk to the power times del I, del j, del k to the power m becomes lambda ij, I1, j1, k1 times del I1, del j1, del k1 times lambda I2, j2, k2, well, and so on. Okay? And where all of the variables are summed over. The alphas are summed over, the betas are summed over, the i's, the j's, and the k's. Now it's an even more horrible mess. But I still have to apply the differentiations to the t's, right? The derivatives to the t's. So, you know, I think of like each of these things as like a pitchfork, and each tine, each sharp edge has to kill one of the t's. But less pictorially, if you apply a differential operator to a product of t's, what happens is that each differentiation picks a t's and eliminates it. So this one would pick this t and eliminate it. And then the next differentiation will have to pick another one of the t's and eliminate it. And then the next differentiation will have to pick another one of the t's and eliminate it. And so on. So each differentiation picks a variable and eliminates it. So you end up summing over all possible ways of pairing the differentiations with the variables. Okay? Now, what does it mean for a differentiation to eliminate a variable? So this is a summation over all betas. This is a summation over all i's. The only way del I1 will interact with t beta with t beta 1, sorry, del I1 will interact with t beta 1 is if I1 is equal to beta 1, and then the contribution will be 1. If you differentiate different indices, if you differentiate t7 with respect to t3, you get 0. Okay? So every time you choose a pairing, you are also insisting that the variable here will be equal to the variable here. Or you're inserting a delta function, a Kronecker delta function, between I1 and beta 1. So now let's read this formula, or this thing written here, as a graph. So really it's a trivalent graph. Here are the vertices. Okay? And then each vertex comes with a coefficient, which is a lambda ijk, and then each edge, so each edge of the graph, like say this edge, comes with coefficients which are two delta functions, one here and one here, and an inverse quadratic for the edge. So each vertex comes with a cubic, and each edge comes with an inverse quadratic. And then the end result can be read from the trivalent graph that you get. So for example, if the trivalent graph was the theta graph, and it actually has to be a fully labeled graph, right? So it has to be a graph in which around each vertex there are 3 Latin letter indices. So I1, J1, K1 here, I2, J2, K2 here, and each edge is marked with 2 Greek letter indices. So alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3. And then the contribution corresponding to this graph is, well, a cubic with the Latin letters I1, J1, K1 here. So this is this. A cubic corresponding to this vertex, this is here. And then a quadratic corresponding to alpha 1, beta 1. But you see, alpha 1 is really I1, beta 1 is really I2. So this, the quadratic corresponding to this edge, is this quadratic here. The quadratic corresponding to the second edge is probably this one, and the last one is that one. So the graph became a contraction of 2 quadratics, so 1 quadratic for each vertex, and 2 cubics, 1 cubic for each vertex, and 3 quadratics or 3 inverse quadratics, 1 for each edge. Okay? And if the underlying graph was a different graph, then a similar thing will simply give a different contraction. Okay? And so the whole integral becomes a summation over graphs, so-called Feynman diagrams. For each graph you have an expression. Here is the expression. The expression in itself is of the form big summation. So this expression here is of the form big summation over many indices. So I1, I2, I3, no, I1, I2, oh no I3. I mean, in the examples we have, I mean, so I1, I2, J1, J2, K1, K2, of some product of cubics and quadratics, so of a product of cubics and inverse quadratics, and that's an evaluation of what we started from. And in fact, maybe I'm out of time, so I shouldn't tell you what would have happened if we had an additional polynomial, so I ignored the polynomial that I should have placed here. So let me ignore this for a moment and go back to where we were. So I want to interpret this for this integral. Okay? So I want to try to compute or use the formulas I got below for the integral dA of e to the I k over 4 pi, who cares, the integral over R3 of R3 of a trace of A wedge dA plus 2/3 A wedge A. Okay? So, and then also times this holonomy, which I'm still leaving mysterious. Anyway, what am I going to have? Okay? So, the I, j, and k of before become points in R3. Okay? Because the summation here is a summation over R3. In fact, they're a bit more than that, because there are also a few discrete indices, because each A has like 3 indices for dx, dy, dz, and the Lie algebra indices, so they become a little bit more than just points in R3, but sort of the heavy thing is a point in R3. So this will become a big summation over Feynman diagrams that look like this, or maybe that, or maybe that. So a big summation over Feynman diagrams. So let's call the diagram D. For each diagram, I'll get messy combinatorics. So messy combinatorics, which I wrote already, which I sort of wrote, but I no point to write it again. But the main contribution is going to be, so for each vertex, an integration over R3, so a multiple integration over R3, and the integrand will be A wedge, A wedge, A, which is something a bit combinatorial, so combinatorial, that's the cubic. I mean, the cubic just becomes something that can be expressed in combinatorial means, times the inverse of a quadratic. Who? The inverse of a quadratic, the quadratic here is the quadratic defined by the differential operator D. Okay? So I need to invert the differential operator. The inverse of a differential operator will be an integral kernel. If you've seen these things, good. If not, just think messy integrals. Okay? But, and now I'm absolutely sketchy and I'm ignoring so many things, but the point is this becomes, I mean, if you do, I actually gave you enough hints. If you do, I mean, enough hints if you're, you know, if you have 50 years to work on it, okay? But basically, these becomes exactly the integrals of pullbacks of differential forms by simply manipulation, by, you know, writing more and more and more equations, you know, A is equal to B is equal to C, but all ideas already appeared, most ideas already appeared. So basically, these become those integrals of pullbacks of differential forms that compute degrees, which can also be computed by counting those cosmic coincidences. And I think that's all I want to say. I know there is no way you could have gotten anything out of this class today other than culture. The only point was to give some culture. So next class we will do something else. Questions, comments? Please forgive me also. Any questions or any comments?
Yeah, so about the holonomy, I believe you chose something from Riemannian geometry?
No. So when people in Riemannian geometry say holonomy, they mean with respect to the, what is it called, the Riemannian connection? They mean holonomy with respect to some connections that arises from geometry. But for me, the connection is completely divorced. So this one form A is completely divorced from Riemannian geometry. It's the holonomy of A, not the holonomy of the metric connection. Yeah. Okay. If you really want all the details, there are, you know, all the classes I gave in 2014, all about this is online. So, you know, you're welcome to watch. Okay, see you on Wednesday. Sorry for today's mess.